And let's see, I'll get into how to translate AI capabilities into better business results. Just a quick word about my background before that. So I've been doing machine learning and AI for about 10 years. During that time, got second place in a machine learning competition out of over 1,300 teams. Spent 3 years as a data scientist at Google. I've done consulting for 6 companies in the Fortune 100. And I'm gonna start with just an overview of what I've seen in our field. So in the last, really, only even just the last 6 years, I think we've gone through 3 different stages. So there was a period of time when data science organizations were allowed to just do experimentation. They didn't need the results to actually feed into real world business processes. And you've seen this is really captured in some sense by well-known projects that didn't really advance business goals. So AlphaGo is one of the most famous AI projects of the last few years. OpenAI had a team spend millions of dollars on compute and take some of the best researchers in the world. And what did they build with that? They built software that could do a better job than the best humans at playing video games. And for a long time, businesses had their imagination captured by the idea that these models were very smart, or that AI was very smart. And they tolerated or even wanted to spend money on data science and AI teams purely for experimentation and capability building. A couple of years ago, 2 or 3 years ago, that really shifted. And I think now at most AI teams and most data science organizations, they are required to at least get their models into deployment. That's become much easier recently, especially thanks to some of these logos on the left are the tools available through all of the major public clouds. So GCP, Microsoft Azure, Amazon AWS, and Amazon SageMaker all have tools that make it easier than ever to take models and get them deployed. Even companies that are not on these public clouds have a lot of great tools to make ML ops easier than ever. And as a result, we see the number of machine learning models deployed has really skyrocketed in the last year or two. But the problem that we are facing as more and more of these models get deployed is that they make predictions for pieces that are a very narrow piece of a more complex problem. So a friend of mine works in data science for a real estate company that owns a lot of hotels. So they've built machine learning models, and they forecast for any given price that we set on all our future hotel nights, how many rooms will we sell? If you had only one night to sell hotel rooms, and you could figure out, we have 10 nights at $150 or 5 nights at, if we set our price at $200, then that would be sufficient to tell you which of those is going to make you more money. But in a world where you've got things that play out over a longer period of time, so for instance, we've got rooms, and whatever we don't sell tonight, we can sell the next day. Whatever we don't sell the next day, we can sell the day after that. Now, these predictions for what will happen in the next 24 hours, they're actually insufficient to ensure we make good, big picture business decisions that optimize things like revenue. And I've found that people who are not data scientists are frequently surprised to realize how limiting conventional supervised machine learning is, and how we're not able to optimize for these dynamic processes. And most processes in the world play out as a series of steps. So data science teams are increasingly finding that deployment is not enough, and they now need to go beyond experimentation, where they were a few years ago, beyond deployment, which is really where we've been recently, to ensuring that their models are useful to achieve not just narrow goals, making accurate predictions, but that advancing large picture business goals that the rest of business cares about. So the steps to that are prediction, which everyone is doing, and then using those predictions, which we get out of conventional machine learning models, to do optimization and ensure that we get practically ideal decisions. So I'm going to walk through the process to do that in a pretty concrete way for one particular example. And this is an example that's quite widespread, and I choose it in part because of both the simplicity and the fact that this is a use case that is very, very widespread for machine learning. But the underlying ideas that you see here will apply for most use cases where machine learning is used with tabular data today. So this is a problem of building a model to handle churn from a subscription service. So this could be a telecom service, or it could be an insurance policy where people pay a fixed amount of money, they get services for some period of time, and the business wants to figure out who is likely to churn. So the common way that we show the output of this model is was a so-called confusion matrix. And for people who are not data scientists and haven't seen a ton of these, the way that that's represented is that we have here two different rows. So we look at our model and we say for people who actually did churn, so that would be this top row, how many of them were predicted by the model to churn? In this case, that could be, let's say, 50,000. For people who actually did churn, how many of them were predicted not to? That would be this upper right, that would be at 10,000. On the bottom row, that's people who actually did not churn. How many did the model predict would churn? That'd be this lower left, 30,000, and so on. Okay, so this is a really common output from a machine learning model where a data scientist will say, here's a summary of how good our results are. This is really, despite being a widespread visualization of model results, this is not very actionable yet. The first step to think about this in a way where we're at least starting to move towards being more actionable is to take these same results. I've still kept the rows meaning the same thing. So the top row is people who actually churn, the bottom row is people who didn't churn. But in the columns, I've replaced the word prediction with do we take action? The key is if we make predictions about who's going to churn, our predictions don't matter. They don't affect anything. What matters is what we do in the cases of people who are going to churn. So a common, the reason we build these models is that we have something that we can do. So for example, that might be we mail some promotion to everyone who we thought was going to churn and encourage them to stay with our service, or we might call them. Both of these come with some cost. In many cases, we'll even offer a promotion and give someone a discount. If we thought they were going to churn, we give them a discount if they stay or if they renew their service. So here the only change we've made is we've taken it from what do we predict to if we take those predictions and take actions on them, how many people fall into each of these buckets. Now, once you've done this, we can get more granular about what we mean by taking action, because it's quite common, or people frequently assume that when we make a prediction, we're just saying what's most likely, because the outcome of whether it's a deep learning model or most other machine learning models for classification is in fact a probability. So if we score everyone of what is the likelihood of that person churning, well, we could say we're going to take action only on people whose likelihood of churn is above some threshold, and we could move that threshold all the way to the left and say we're going to take action, run a promotion to everyone. We could move it all the way to the right and say we're only going to take action and promote to people who are on the very highest scale for being most likely to churn. And so in that sense, that simple view that we had in that table of who do we take action on, that's something that we now have a lot of control over, because we can take the outputs of the predictions from that model and determine what's the criteria that determines which people we take action on. All right, so we still are not yet optimizing to ensure bottom line outcomes. So how do we do that, given the fact that we can take the predictions from that model and do something more with them? So the thing I'm about to show you is sometimes called profit curves, or sometimes called revenue curves. And it's a pretty simple technique. So in a moment, I can talk about things that are more sophisticated than this. But this is simply to say, we evaluate for each individual. Let's say they're an individual that actually we're going to churn. What do we think the value to our business is of taking that person, they were predicted to churn, and now running a promotion? So in this example, I've said, let's say it's $10. And that's the sort of thing you're just going to have to talk to someone on your team, and you can figure out what is the value of given someone's actual outcome, which you can use validation to or cross-validation to figure out how many people are in each of these buckets. What's the value of running a promotion? On the flip side, you could say someone who wasn't going to churn, if we run a promotion to them or take action and we do it unnecessarily, what is the cost of that? All right, so this table in the bottom is sometimes called a cost-benefit table. You don't need the column on the right to be zeros. You could assign that other values. In practice, the only thing that's going to matter for the decisions that I'll show you how to make to ensure better business outcomes, the only thing that matters is the difference between this first column, the yes column, and the no column. So it's quite fine to normalize that second column to 0. And now we can evaluate what is the business benefit of running a promotion based on the output of our machine learning model, where we use a given threshold. So we use a given threshold. That threshold determines how many people we run a promotion to, and as a result, determines all the values in this top table. And we can simply do some numeric calculations and say, if we use that threshold, in this case, we'll run a promotion to 50,000 people. We, on average, have a valuation of $10 per person for running that promotion. We subtract off the 30,000 people who we unnecessarily ran that promotion for. Maybe it's just a mailer we sent them. And that means that in this case, we got a valuation from running this promotion. When I look at all the people who we correctly ran it to, as well as those we needlessly ran it to, we can just do some subtraction, and we see that the value of that is $470,000. We're still not, we now have a way of measuring the value of using a machine learning model to target a population and then run a promotion based on that. But we're not yet optimizing. So the way that we ensure we are getting the best business outcomes possible, given this, this framework that I've laid out, is to now, for every given threshold, say, all right, what if I run a promotion to everyone who's at least 1% likely to churn, or 2% likely to churn, and 3% likely to churn? For each of those thresholds, each of those decision thresholds, I will get different values in this table in the top, because I'm changing the population of who I actually send the promotion to. Every time I change these values on the top, I can just do some numeric analysis and figure out what is the what's the benefit of running the promotion to that population. And now I can trace out what is the value to my business of running a promotion given any specific decision threshold. Okay, so what have we done so far? First of all, I mean, the mathematics of this is actually pretty simple. A data scientist who writes code in Python regularly could code this up in minutes. But we've done something which is far less common than it ought to be. We have gone from, I've got a machine learning model, it makes predictions. What do we do with those predictions? You know, typically people sort of guess about what to do, or the data scientist does something which seems reasonable, but really is a strategic decision that they put far too little thought in. They focus so much on making predictions. And now we can rigorously optimize for what is the ideal decision-making rule that we use as the, once we have those predictions about, in this case, who's going to churn or not churn. So the advantage of this approach, like I said, it's something that can be coded up in minutes, is pretty simple, and is broadly applicable, but with some really important limitations. So the most important limitation, and we could talk through in a bunch of use cases, the most important limitation is that this machine learning model captures such a small fraction of a large picture business process. And again, people who don't work a lot with data scientists are really, as they become closer to understanding the capability of machine learning are frequently really surprised by this. But machine learning predicts something that is very narrow and very specific, and that's realized at a point in time. And so in most business processes, they're very, very complex. And as a result, we could have this, in this case, it's a manufacturing setting, we could have this manufacturing setting with all sorts of relationships that play out over an extended period of time. And the thing that we do with a machine learning model is to predict something that's very narrow and very specific. And that's is not a shortcoming of the way that we do data science. It is an inherent statement about the way that deep learning models or neural networks work. It's a statement about the way that gradient boosting models work. It's a statement about the way that random forest work. They predict things that need to be very narrow. We would like to change to a world where we can do what is over here on the right, where instead of just predicting one narrow piece and then coming up with sort of a best guess about how to use the predictions for that in order to optimize for a big picture business KPI, we'd like to build a model where everything that matters, from the thing that we control all the way down to our business level KPI. I think it is very important that we specify a business level KPI, because you frequently see data scientists who want to optimize for sort of model accuracy. But we want to build a model where you can say everything that matters is all accounted for in some way. That is certainly not the case if we go back to that cost benefit table. There, we just really had a best guess for what's the value of running a promotion to any individual. And it wasn't necessarily calculated by in a particularly rigorous way. To pursue this broader vision of what it means to build a model, you need to integrate multiple machine learning models, because again, those machine learning models predict things that are very specific, and we've got a complex process that involves many interacting parts. And then there are many parts of your process where you're going to need to just collect domain expertise. The data scientist talking to someone in manufacturing, or the data scientist talking to someone in marketing, and then bring all these pieces together into one holistic model, so that now I can say, given this holistic model, if I change labor, if I increase it a certain amount or decrease it a certain amount, what is the impact that has on production, and what's the impact that has on sales? What's the impact that the change in sales has on revenue? If there's some cost of transport, I want to build all of that into my model, so that now I can try out different decisions for my labor and actually see the bottom line outcome to an outcome like holistic profit, in a way where these models are no longer siloed and our decisions are no longer siloed. To give you an example of what that looks like in this churn example we talked about, that could be for every customer, I say I can put in a given amount of promotional effort. That's going to influence, for that particular customer, does that customer leave or not? So we could have a machine learning model that predicts that. That could influence the revenue. If I cut them a discount, I could embed just a formula for what's the revenue that I make with that promotion, what is the revenue without it. Maybe there's a fixed cost of providing services. And now for each of these arrows, the arrow from promotional effort to does the customer leave, that could be something that I estimate with a machine learning model. These other arrows could be summarized in just equations. And now I have a system of equations where I can figure out, for each customer, do I make more profit if I promote to them, or do I make more profit if I don't? And we now have a specific, individualized, personalized, what is the ideal thing to do for this customer in order to, whatever, if our goal is expected profit, then to optimize expected profit. So I'll walk through a very quick example. I won't walk through all the numbers, but just I'll say enough so that you can see how it works. So we could have a single customer here, and we have a program that says, or a model, and it says, what happens if we offer this person a promotional discount? What happens if we don't? The first column is, what's the probability of that person staying with our service? So that's something that we can estimate with a machine learning model. Profit, if they stay, that could be, let's say it's $100. And now this is just multiplication. our expected profit in month one, if they stay, is $90. Do the same thing for the subsequent months. You can add it up and we can see that if we offer this person the promotional discount, we make 450 bucks in expected value. We could, on the other side, say, what if we run this promotion and we don't offer, what if we don't offer that person the promotional discount? Now we make more money, so you see profit if they stay. Because we're not offering them a discount, that's a higher value. The probability of them staying, because we're not offering them a discount, in each month is lower. So for instance, 80% instead of 90%. And this value could come from, again, a machine learning model that predicts the churn rate. Or we do some, again, simple multiplication. And in this case, we could add that up and say, for this individual, we make $498 on average if we don't offer the discount. And now we've really gone from, we made a prediction and then we didn't really have a way to say concretely what gets us a better big picture business value, to now we're just deciding, do we want to make $450 on this customer or do we want to make $498? If you consistently make the better decision, and in this case, you make about 10% more, that's going to have a huge impact when you do that at some scale. I've walked through a quick example that was related to churn. Where is this useful? So our company, Decision AI, builds a piece of software that allows you to integrate multiple models and provides a nice layer to do this. The places where we've seen this used, and I should also mention, you can do this without our software. You can do it in, a data scientist can do it with a lot of the tools they have today. A lot more effort, and so there's some shortcomings to that, but it can certainly be done. Where is it used? So one of the most obvious places is pricing. I gave an example about a hotel. They would like to know, for any given price we set today, what's the impact that it has on how many rooms we sell, as a result, how much revenue we make today. But in turn, how does that affect our competitors' price tomorrow, which in turn affects how many rooms we sell tomorrow, which in turn affects our revenue tomorrow. And you can do that same calculation and say, for any given pricing rule, how much will we make before the night of the stay? So we've seen this in hotel pricing. We've also seen it for insurance pricing. So it's quite useful for pricing. We have a use case we're working with someone for fraud prevention, helping them do a better job of prioritizing which transactions they manually investigate as being potentially fraudulent. We see a lot of people today who have a simple machine learning model, and they just say, every transaction that comes in, we score it, and if it's at least, let's say, 5% likely to be fraud, then we take some action on it, or we investigate it. That particular rule is particularly naive. That means that if I have one transaction for $1,000 and it's 4% likely to be fraud, and one transaction for $10 and it's 5% likely to be fraud, we'll prioritize that $10 transaction over that $1,000 transaction, which is just, it's just costing you money. And so doing a better job of figuring out those rules for what do we investigate as fraud. There are a lot of layers to that, even beyond accounting for the dollar value of the transaction. We see this in product recommendations. You probably should not be recommending just the thing that someone's likely to purchase or click on. You should think about the dollar value. You should think about which items would they buy lead to customer lifetime value and customer loyalty. That's, again, something that you can model. See it in preventive equipment maintenance, supply chain management. So I found that in about 80% of machine learning workflows with tabular data, so I'm excluding robotics, excluding computer vision, but in about 80% of use cases with tabular machine learning or machine learning on tables of data, you'll get much better business results if you formally model what happens, not just in the machine learning model, but formally model what happens after that. Data scientists have been very focused on machine learning, and as a result, very focused on predictions. And this workflow is unfortunately just not common enough. And I think the payoff to really taking this seriously is far greater than the payoff we had even over the last few years of improving model quality in the sense of making more accurate predictions. So Yeah, happy to answer the rest of the time, and happy to answer questions anyone has about this workflow